Thanks very much for the organizers, my colleague Edo and John, and also my fellow speakers and colleagues who are here to share their wisdom. It's wonderful. I'll just start with an anecdote that the first city I actually landed when I came to the United States a while ago. Okay, I'm getting old, but still, the first city I landed is in Philadelphia. So it's always close to my heart every time I visit the city. So I have been working last several years or so on problems related to climate. I'm also part of the Harvard University Center for Environment. And I thought I'll just share with you a couple of vignettes from my work that many of you may find parallels to in working in the financial industry. And I thought it would be good to, maybe it'll stimulate further conversation. I'm around and look forward to chatting with you post this talk. So I'll just give you both the outline of what those two vignettes are. These two are two different projects done with students and colleagues, but they all have the underlying problem is the same. It's related to what my Jun was talking about. It's the measurement error problem. So, and I will, after I outline the applied problem and how we solved it, and maybe I'll just take a minute or two to explain my perspective on what the parallels are in the financial world also, and I'd like to know more if that resonates with you. Okay, so the first problem is about uncertainty in the sea surface temperatures in early 20th century. And this is, by the way, joint work with Chen Guang, who is a former PhD student with Jun and also worked with me. Now he's actually in the financial industry. And Duo and Peter is a climate scientist at Harvard. So this is data that is obtained from this repository called ICOADS. I'll tell you a little bit more about it. This is where, this is where everyone goes who works in this field to get the data from. And so if you think about it, this is what the data looks like. This is data actually from people that collected that went on ships. And this is in about 1885. I don't remember which month, in 1 month, right? So each of the tracks that you see, ignore the colors for a minute, each of the tracks that you see is actually the ship trajectories. Now, mind you, these are not the actual temperature measurements, these are just the ship trajectories going across Atlantic, right? So you would wonder, in those days they didn't think about climate change. So you'd wonder why would they even, collect temperatures? How were they incentivized? It turns out that the East India Company apparently had good knowledge of the ocean currents, and so they sort of traded them. Like, say, most of these were commercial ships, so they told them, like, you collect the temperature and give it back to us. We'll tell you a little bit more about the ocean routes and the currents, etc. Okay, so until about when I was working on this project with Peter and students, many people have studied this data, and many of them had, many scientists had worked on this problem before, and there are lots of issues, right? This is a very humbling problem. You need all hands on deck. And the main issues that people thought about were, they were not really scientific about measuring the temperature. They would just insert a bucket into the ocean, collect it, to put it on the ship deck for 5 minutes, I don't know. And then if it's a warm summer month, then it may get warmed up, right? Similarly, it matters where you collect the temperature. If it's the ship room is in the basement, maybe it's on average, it's warmer there, right? Anyway, so there are lots of different issues, but all of them assumed that the measurement of the temperature was taken at the place that it's recorded, right? In the ship tracks that you just saw. No one questioned about the integrity of the data at all. They just assumed that was what was collected. Now, let's look at the data again closely. So apologies to the colorblind. There are 3 colors there. Ignore the green. So let's focus on the blue and the yellow. So the blue ones are ship trajectories. Again, these are ships that stopped every 2 hours and collected the temperature. And the yellow is the one that is ship trajectories, again, where the ship stops at every 4 hours and collected the temperature. So first look at you'll notice that the blue trajectories definitely have breaks, and it's not really surprising because the large jumps that you see, is it because, well, they didn't have GPS or iPhones or any other way to measure the location at sea, right? So the way they did that is in the midnight, they will just look at the sundial and the charts and just look at the position of the sun or whatever. I mean, I don't understand the science of how they did that to sort of recalibrate where their location in the sea is. But I just want you to focus on the yellow ones, right? And this is the starting point of our research. If you really look at the yellow trajectory, I don't know about you, but for me, it's too straight just a straight path to be an actual ship trajectory. So, and we believed, and my fellow scientist colleagues agreed, that this is actually unreliable. Some people use the word fake. I wouldn't use the word fake, but totally unreliable. Like in the sense that any reason, and that's actually also evident from the blue trajectory, right? Which is that any actual reliable, any reasonable ship trajectory across Atlantic, you will expect so much randomness and so much waviness that you don't expect this straight line. There is reason to believe why this could be, because these were digitized from the actual data from early 20th century. Many hands have gone on to getting this data, et cetera, right? So notice that, again, I'm not going to come here and say, I deny climate change or whatever, especially I'm on video. That's not the point of this talk. I wanted to just focus on the data integrity issue, and maybe this is the time to talk about the parallels, right? In the financial industry, I know that many of you pay a huge amount of money for getting data from a third party, and also often terabytes of data. And I wonder how you really do this exercise where you really think about how good the data is, because it's an important part. It's an important ingredient in everything you do, and it's especially coming from the third party. How do you just verify the integrity? Anyway, so here, the important story is that, well, clearly, I'm not going to I'm considering the yellow data to be unreliable. So, but these are the actual places that people thought we were taking the measurements on. And most importantly, these are the actual data in which our current knowledge of what the earlier 20th century sea surface temperature is based on, right? So any source of uncertainty in this position at which the temperature was measured will be reflected onto our understanding of how the temperature in sea or ocean was in earlier 20th century, and that has implications on what the current ongoing debate. Okay, so and maybe just a couple of more points on the scientific, why is there reason to believe this? This is a well-established field in the ocean science that the ship has error because of the wind and the random angle that the ship takes. The ship is essentially performing doing a random walk, just bombarded by the wind, right? And the errors accumulate. The other thing is that, and this is what I just told you about the celestial correction, where they just do this once a day. I just wanted to point out that maybe even slightly earlier, this was in about late 1800s, during about that time, maybe in the late 1700s to early 1800s, finding the longitude in the sea was, at least latitude, they could do the celestial correction, but the longitude, finding that was one of the most challenging problems of their times. And this guy, Sobel, I don't remember the French engineer who solved it, and the way they did that is inventing very sophisticated clocks, and they did that. So it's worth a read. Okay. So again, even if you've zoned out for a minute, I'll just put you back in saying, so we have data sets. These are the actual data in which people thought the ships were moving, and if you look at the data closely, there is reason to believe that at least some part of the data is not reliable. Okay. So what we wanted to know is, okay, what can we really do to understand this uncertainty, quantify this uncertainty, go back to what does that translate to the uncertainty in the temperatures, as we know from early 20th century. And by the way, how much of this data is of this quality? You can see this is in one summer month, right? And about at least 20 to 30% of the data is of this yellow kind, which is totally unreliable. At least the blue ones, I can take that. Okay, at least I can work with that. The yellow and pretty much everything is like this. And this is for 1 month in 1 year, and we have about 150 years of direct temperature measurements in which at least quite a lot of, a significant part of the data set is of this quality. And what is also surprising is that despite being intensely studied by various groups, and no one had questioned about this particular aspect, right? And it's worth discussing. It's worth pondering. So now I almost feel like a weatherman, but I still should make this point. That why do you care about the uncertainty in where you measure the temperature? It's because even if it doesn't say a lot about the global warming or whatever, it says a lot about the events that we care. So for example, the red thing over there is the Gulf Stream, right? So depending on where you measure the temperature, the gradient there is large. So if you measure on one side, whereas in actuality you're measuring on the other side, you'll get vastly different answers. And these are questions that people care about. If you look at New York Times, the last week even there was an article about how the Gulf Stream has evolved over time. And our point is that to answer those questions, we really need to know accurately what happened before from the limited data that we have. Okay, so I don't want to get into the, it's too early in the morning for equations, and also Jun has showed us quite a lot, so I thought I'll just skip a lot of that and just tell you the main idea behind this. So we wanted to do, look, there is a simple way you could do, and this is where classical statistical methods shine. They just tell us how to quantify uncertainty in a very simple but reasonable way. So all I'm going to assume is that on the yellow tracks, I'm going to assume they left on this port on this day, and they reached the other port on this particular day, let's say in 2 weeks. That is all I'm going to assume. And in between, I'm going to assume that they were moving according to some random patterns that ships move. Of course, you can't really assume anything. You need to know what roughly the average ship, the speed of the ship in that time was, what was the wind speed, etc. But this is where the generations of classical statistical work actually tell you. So there's this idea of Bayesian hierarchical models. Again, many of the people and colleagues in the audience have made seminal contributions to this. You can really use the idea of borrowing information in that we have data, especially the 2 hourly tracks, that actually tell you how you can just actually calculate what the average the speed of ship in those times were. Which traveled in similar months from similar ports. You can also measure, you have some reliable measurements of the wind speed was also. So using this, you can just really create a simple statistical model and ignore the equations. These are just saying distance divided by time is equal to speed. That's all this means. The cosine and sine angle that you see is because of converting the spherical coordinates to the map, the cartographical coordinates, right? So because Earth is, so just basically that geometry is what you see. There's nothing else there. And one more point about, and this is what I just said, there's this machinery of hierarchical models just really tell you that we have many similar ship tracks. There is valuable information that is contained in them, even though each individual ship track will not give us that much information. When you combine them in a judicious way, there's quite a lot that you can leverage. People who have not worked in classical statistics, maybe this is something worth paying attention to, that this is a paradigm that is pervasive throughout statistics and no doubt useful in a large number of other contexts. I just take a word about computation. So there's also sort of an activist community in statistics who make these tools that are publicly available that people can, so this is a very powerful program called STAN where you can just download this and fit models with little to no effort, maybe half a page of code. on the model that I showed you, right? You just give it data and these give reasonable statistical models, it will just give you, what is most important about this is that it will give you reproducible results. That we wanted this method to be applicable. I want it personally for my fellow climate scientists to take this and use it for other problems where they think there are similar issues with the measurement error. I'll just show you the results. So one result is that the uncertainty at the ship track is quantified. It's not surprisingly, you'd expect that the uncertainty is the most when the ship is in the middle of the ocean, because at ports there is absolutely no uncertainty. We know they left here this day and they reached there on that day. In the middle, the uncertainty is the largest. And what this, now the final point of this first vignette is that this is on the left is the actual computation of sea surface temperatures, accounting for the uncertainty in the position. On the right is where the sea surface temperatures without accounting for the errors. And then you really do see quite a lot of difference, maybe about a degree or so, especially when there is the Gulf Stream. And you can really see, right, like 1 degree Celsius increase is quite a significant, of significant importance to that community. Right? So I just wanted to pause before I go to the next vignette, that the point I wanted to, this all came from just questioning the integrity of the data and also incorporating domain knowledge, and the scientists agreed that, yeah, there is reason to believe that the data is really not reliable and we have to do something about it. And the hope is that we are, and this is, again, the problem is also humbling because there's so many other similar sources of, different sources of error. So what we're planning to do is to correct for using statistical methods to correct for all known methods and release this new Harvard climate data set where other researchers can use. Let me just, in my remaining time, let me just show you a different vignette. This is with a different group of people. Again, Peter is my partner in crime from the climate Earth and Planetary Sciences department at Harvard. Maxime was a PhD student at Harvard. Now he's working for a climate startup. And Karen is a professor at UCLA, who is a former PhD student at Harvard. So here is the problem. This is a really fascinating problem. So this is a set of temperature measurements at a field in Iowa in about 2015. Okay, so this is the actual temperature. And what people are interested in is the daily maximum and the minimum. And every day, this is the diurnal cycle, and people want to know, climate scientists want to know how this varies across the year, right? Like is it and how does the difference between the maximum and minimum changes? Now here is the fun part. Believe it or not, even today, despite having easy availability of highly sophisticated sensors, the actual way the measurements are collected is that volunteers go to these fields and collect the temperature once a day. All right, and I don't know what time, we don't know what time they collect, but that even more importantly, what is funny is that the machine which records that, it records only the maximum and the minimum in the past 24 hours. And this is the most important part of this particular vignette. So I'm going to take 1 minute to make sure that the problem is communicated correctly, because that is far more important than my own solution, because I want to know how you would think about the problem, right? So let me tell you again one more time what happens. So what happens is that you go there. So I'm a volunteer. I go there once a day, let's say 10:43 p.m., 10:43 a.m., 10:43 p.m., I'm ready to drink already, 10:43 a.m., and you get to see the maximum and the minimum in the last 24 hours. So let's understand, is there a pointer here? If not, I'll show you. So imagine that on April 3rd, 2015, right? Yeah, so April 3rd, 2015, that was an unusually cold day compared to the previous day. Do you all see that? Right? Therefore, the machine would falsely record the maximum to be the previous day's maximum, where in fact, what you really want is the red peak of the April 3rd that you see, that you miss, right? So because that April 3rd was an unusually cold day, the previous 24-hour maximum is different from the actual maximum of that day that we want to measure. And moreover, this depends on when you collect the temperature too, which also we don't know. By the way, this should come as a real surprise. This is present day, like this is not made up story at all. And for the last few decades, this is the quality of data that we have. Okay. All right, so what is the scientific problem, of course, is that we want to know what is the maximum temperature in the day and what is the minimum temperature in the day, and how does this change across the entire year? And how does it change from time and how in time and space, right? That's what we want to know. The the statistical problem here is that what we observe is this curve of the maxima and minima observed in the last 24 hours. And from this, we need to reconstruct what the actual temperature patterns were. Right, this is the problem. This is, again, a missing data problem, but a missing data problem with a real twist in the sense that you have observed a minima and the maxima. That's what people see. So again, what is currently done and what the weather services use is that they take the maxima and the minima of this curve, right? That's the current state of affairs. So you can see that we know that can't be correct because of what I just showed you in pictures, right? So any improvement for this will already go a long way in helping this. So, and this is now time for my second vignette and connection to the financial services, the financial world, is that you can probably use different sources of data for solving this problem, right? So our approach was that you can really look at, the field at Iowa that I showed you is just really terrible data quality. We don't have any data, forget terrible data quality. But we can really look at the nearby airports. Now, airports really do keep meticulous temperatures. But the problem is that the airport's temperature is also on average warmer than the nearby fields because of human activity, raise temperatures also, right? And also that airport temperatures data is it's very unreliable in the sense that they are constantly changing land use. Oh, thank you. That's okay. They are constantly changing, right? They are creating new runways, expanding space, etc. So what used to be a field, even in an airport, now is currently concrete, so the temperatures are different. Yet what is important here is that the information is coming in terms of the covariance, right? In the sense that if you really look at a nearby airport and a field, they are probably correlated. Like the means, the average temperatures at both places are different, of course, but the covariance is you expect it to be more or less, closer than, let's say, airports or points at vastly far away locations. So the hope was that we could really use this information. This is an additional source of information, albeit noisy. You can still use it towards reconstruction of what we wanted. And that's what we did in this problem. Again, classical statistical methods help. The huge, Jun already talked about Gaussian processes. There are the spatial methods that tell you how to do this. I'll just go over these quickly. So these are classical function interpolation methods, if you want. And I'll just show you some pictures. So these are the actual, this is a place where you actually know what happens so that you can benchmark our results. So this is what happens when you fit a curve using nearby temperatures, temperature data from nearby airports, and you really compare it to the actual data. They don't work, they're reasonably good, but not as good, right? But of course, we haven't used all of the information that we have yet. What is the last piece of information we haven't used? Well, the volunteers went ahead and collected the data, and they still have the actual maxima and the minima in the last 24 hours. It turns out that to incorporate that constraint is an unstudied problem in statistics, right? And after this is a case I've seen it before, where sometimes when you really look into these problems, that you can abstract out some hairy statistical problems that we don't know how to solve, or at least we haven't thought about because we didn't have occasion to. So here is a problem. So the new wrinkle, and I'm deliberately going fast because I don't want to take too much more time. So the new wrinkle is that in addition to using the airport data, you have to use the fact that you already know the past maxima and the constraint imputation problem, where the maxima and the minima has to be consistent with what we observed in the data. And it turns out that that is equivalent to a very interesting sampling problem. I can talk to you offline if you're interested in it. And here are the results. Again, you can see that we managed to solve this problem. And you can see that you can, of course, impute the curves using even if you've zoned out the last 10 minutes, here is what you should take from this second project. What we have done is you use the nearby airport data and the information of what the maxima and the minima to reconstruct the temperature curves at a reasonable level of accuracy. And as you can see, the curves necessarily just touch the red and blue curves exactly once, again, being consistent with what you observe. And if you really look at now you go back to the original problem of what the constraint, what is the diurnal cycle, like how does the maxima and the minima temperature vary across different times? We get far better accuracy than what is currently done. I agree that the current technology is so bad that I don't even want to use it as a straw man to beat. But yet, any reasonable statistical method would actually go a long way. So I'll end this second vignette by saying that and I hope many of you find parallels, and this is the part I'm most interested in, is chats later on. I'd like to know how you would solve this problem. Secondly, that I'm sure you have similar experiences where you use some other noisy data to solve an important problem, and I would like to hear the experiences. So I'll just end the talk by saying, I've really enjoyed working in climate science. It's really a fertile ground for interesting, both applied problems, but also the problems that come in my own field of statistics and sampling, et cetera. And of course, the more I think and talk about it, the more I see parallels to the financial world. So thanks very much to the organizers of Wells Fargo, my colleagues, and look forward to the rest of the talks and look forward to the conversations. Thanks very much.